Okay, let's solve this problem. Last time we calculated the final temperature of the system, and it was 19 degrees Celsius. So today we are going to calculate the total entropy change for this process. So we have a copper and water together. So the way to calculate the change of entropy can be done by this way. The change in entropy is going to be the change in the entropy of copper block plus the change of entropy of water. So that's how we can calculate the change of total entropy. So let's calculate the change of the entropy of copper block. So how can we do that? We can calculate this by mass times the specific entropy at the final state minus specific entropy at the initial state. What about this water? We can do the same. The mass of water times the specific entropy at the final state minus specific entropy at the initial state. And from the TDS relation that we studied last week, we know S2 minus S1 for solid or for liquid. We can calculate this by specific heat, natural log T2 over T1. So that's how we can calculate the change in specific entropy. So let's do the same. Mass of copper block, which is 75 kilograms. So 75 kilograms times specific heat C times natural log T2 over T1. What about the change in specific enthalpy of water, mass of water that can be calculated by the density 996.5 kilograms per cubic meter times the volume 0.16 cubic meters. So that's how we can determine the mass of water multiplied by specific heat C times natural log T2 over T1. So what is this C? The specific heat. Do we know specific heat? Yes. Copper block specific heat is 0.385. So this one is 0.385 joule per kilojoule per kilogram degree Celsius. What about this specific heat of water? We can select the specific heat at 300 Kelvin room temperature. The value is 4.179. So this C is 4.179 kilojoule per kilogram degree C. What about T2 over T1? T1 is the initial temperature of the system. So what is the initial temperature of this copper? 110. So this one is 110 degrees Celsius. What is the final temperature? 19. So this T2 is 19 degrees Celsius. What about the initial temperature of water? 15 degrees Celsius. What about the final temperature of the water? 19 degrees Celsius. So that's how we can calculate the change in entropy. Then if you calculate the sum of these two, you get 1.36 kilojoule per Kelvin. That's how you solve this problem. Is this correct or there's a mistake? Yes, the temperature should be in Kelvin. So this is going to be not 19, it is 292 Kelvin, not 110, it's going to be 383 Kelvin. This one is 292 Kelvin, this one is 288 Kelvin, okay? Any question about how to calculate entropy change in a solid or a liquid? No? Then let's look at the last slide for finding entropy S. So this time we are going to talk about ideal gases. Then how can we calculate the entropy change of ideal gas? We can start with the TdS relation. What is the TdS relation? TdS relation, we can start from, we derived up to here. So ds is du over T plus pressure times dV over T. If you're not sure what it is, we got this equation from the energy balance equation in a differential form, which is del Q minus del W is going to be du. If we take this in a reversible system, then by the definition, ds is del Q over T. That is the definition of entropy. Then we can say del Q is TdS. Yeah, we can do that. What about the work? Work can be determined by pressure times volume, TdV. So this equation can be written as TdS minus PDV is du. Then you can divide each term by temperature T, temperature T, temperature T, and divide by mass, mass M. And we can move PDV to the right-hand side. Then we get temperature, temperature, temperature stays here, mass, volume, so it becomes specific volume, mass, entropy, so it becomes specific entropy, mass, internal energy, so it becomes specific internal energy. So this equation becomes ds is du over T plus PDV over T, which is the equation you can see right here. Then, this is a differential form. So if you want to calculate entropy change, how can you do that? You need to integrate from the initial state number 1 to the final state number 2. So we just need to integrate them. And then how can you integrate? First, the integration of ds is pretty simple. It is just S2 minus S1. What about here? Oh, this one is not simple because we have two variables, u and t. So what can we do? We need to find the relation between U and T. And from chapter 3, we studied one equation, which is specific heat equation. U2 minus U1 is CV T2 minus T1. In a differential form, this is going to be the change in U is going to be CV times the change in T. So du is CV dt. So we can replace this du with CV dt. Then this equation becomes from 1 to 2 CV dt, which is du divided by temperature, divided by temperature. What about here? Can you integrate this one? We can't, because we do not know the relation between pressure, temperature, and specific volume. So we need to come up with another equation that has pressure, temperature, and specific volume. Do you remember any equation that has all three? Yes, the ideal gas equation that we studied in chapter 3. PV is RT. So let's look at this equation. We have a P over T. So can you make P over T? Yes. By how? By dividing by temperature T. What about this V? Let's divide by V2. T times V. T times V. Then let's see what we have. VV can be crossed out. Temperature, temperature. So what we have is T over T is going to be R over V. So we can replace this P over T with R over V. Can we do that? Yes. And let's see. Plus integral from 1 to 2 R over V. R times dV over V. Now, can you solve this one? We can solve that equation with one condition. That condition is going to be, I'm going to assume CV, specific heat, is constant. So this is the assumption. CV is constant. If you assume CV is constant, this one comes out. What about here? Can you integrate this one? Oh, it depends on this R. If R is constant, this one comes out. If R is a variable, then we need to find the relation between R and V. So, is this R constant? Yes. The name of this R is gas constant. So this one comes out. So now, can you integrate this one? Integral dt over t or dv over v? Yes, we can. If you don't remember, integral from 1 to 2 x, I'm sorry, dx over x is going to be natural log x from 1 to 2, which is natural log x2 minus natural log x1. Then you can combine these two, natural log x2 over x1. So similarly, we can do that. We have a CV in front. So this equation becomes S2 minus S1 is CV times integral dt over t, integral dx over x. So it's going to be natural log t2 over t1. Natural log t2 over t1. What about here? This r comes in front. And what is the integral of dv over v? The same thing, natural log v2 over v1. So this one is natural log v2 over v1. And this is how we can determine the change in specific entropy. But that's not the end. Let's go back to this equation. And ds is dU over T plus PdV over T. Then, in chapter 3, we studied entropy H is U plus PV. By the definition of enthalpy, enthalpy H is going to be specific internal energy U plus flow energy P times V. Then, what is the differential form? You can add a D in front. dH is du plus d of P times V. Then what is d of P times V? dH is going to be du plus PdV minus VdP, a plus. Then, if you look at this equation, we have du plus PdV. Here we have du plus PdV. Then, can we move this one to the left-hand side? Yes. Then, dH minus VdP is the same as du plus PdV. Then here we have du plus PdV. So we can replace du plus PdV with dH minus VdP. So this ds equation is going to be dH over T minus VdP over T. So these two are the same equations. The first equation has internal energy U. The other equation has enthalpy H. Then, can you solve this one? Yes, you need to integrate again from the initial state number 1 to the final state number 2. So let's do that. Then, can you integrate this one? Well, it depends. If we know the relation between T and H, then we can integrate that. What is the relation between T and H? From this one, specific heat equation, H2 minus H1 is Cp times T2 minus T1. Differential form, this is going to be dH is Cp dt. So this can replace this dH. What about this VdP over T? We can use the ideal gas equation one more time. PV is RT. Then V over T can be found by dividing by temperature T. And let's divide by pressure P. Then P go away, PT go away. So V over T, which is this one, is R over P. So this R over P is going to replace V over T. Then this equation becomes integral from 1 to 2 ds is integral from 1 to 2 Cp dt over T minus this one R dP over P. Then can you integrate that? Yes, we can. This one is going to be S2 minus S1 is Cp comes out. We assume that specific heats are constant. Cp is constant. Then if you assume Cp is constant, the Cp comes out. So Cp times the integration of dt over T, natural log T2 over T1 minus this R comes out, R natural log T2 over P1. So this is another entropy equation that we can use. So we have one equation here, another equation here. Both we assume specific heats are constant. Then sometimes, we have a problem whose specific heat changes dramatically. Then how can we solve those problems? Then we assume that Cp is not constant. Then this equation, the problem is this term. If Cp is not constant, we cannot solve this. So we are going to use a table. In that case, S2 minus S1 is going to be S degree 2 minus S degree 1 minus R natural log T2 over T1. Then how can we find S degree? We can find them from a table. So these are three different ways to calculate the change in specific entropy when you have an ideal gas. The first one, we can use the first one if you know the relation between the initial volume and the final volume. You can use the second equation if you know the relation between the initial pressure and the final pressure. You can use this one if you cannot assume constant specific heat. So these are the three equations that we are going to study. We are going to use to evaluate the change in entropy of a gas system. Yes. Oh, this one? You're right. Temperature. Thank you. My bad. Monday's sickness. Today is Monday for me. I had no class yesterday. Any question? Then you should have one question. Do I have to memorize all of them? Not necessarily. You just need to memorize this one and this one and this one. Three of them. And just to make sure that you know when to use, the what. Okay? So basically, if you can assume constant specific heat, you can use these two. Then which one you are going to select? It depends on the information you know between the initial and the final state. If you know the initially pressure was this one, finally pressure is this one, then this will be much easier than using this one, because in this case you need to recalculate volume, right? So depending on the properties that you know, you can select one of these two. If constant specific heat assumption is not valid, then you can use this equation, and S degree can be found from a table. Then, which table? If it is on air, you can use table 820, but we have a problem later, so we will see what table we can use. And when we go to chapter 9, and we are going to, redo how to find, the S degree at the time. And if you go to Thermodynamics 2, then, the finding S degree is very critical. So we will revisit this S degree there when you go to EGR356 heat transfer. By the way, if you plan to take EGR356 next semester, I won't be here because I will be on sabbatical. So someone else is going to teach. I think Dr. Malik is going to teach that. Any question about this slide? No? Okay. Then before going forward, let's discuss these equations a little bit. Why do we study entropy S? Because entropy S can be used to to study one thing which is reversible process. Entropy S is the degree, is a thermodynamic property that shows how much useless energy is created during a process, right? So when you convert electric energy into thermal energy, we say entropy has been increased because electric energy is useful, thermal energy is not, right? Then how to make an efficient system? You can, make your system as close to an ideal system, which is reversible system, right? Then how do we know when a system is reversible or irreversible? You can calculate entropy change between the initial state and the final state. If entropy does not change, that means the process is reversible because no useless energy has been created because entropy remains constant. So one of the things that that we want to know, while studying entropy is going to be what is the process whose entropy S remains constant. That is called isentropic process. Isentropic process means entropy remains constant. So the change in entropy is going to be zero. Entropy at the initial state should be the same as entropy at the final state. That is isentropic process. Is it possible in reality? Probably no, because in actual system, there's always some degrees of irreversibilities. Then how can you make an efficient system trying to minimize those irreversibilities? Meaning is that, trying to minimize the increase of entropy. That's how you can make an efficient system. If this battery lasts 8 hours, if you, minimize the entropy increase of this battery system, it may last 10 hours or 12 hours trying to decrease the increase of entropy. So when you design the engineering product, our focus is going to be how we can make our process close to an isentropic process. To do that kind of analysis, we need to know how to evaluate an isentropic process. So let's do that. So let's study this isentropic process. I'm going to assume we have an isentropic process. Then how this equation is going to change? If it is an isentropic process, S1 is the same as S2. Oh, we have a S2 minus S1. So when we have an isentropic process, the left-hand side of this equation is going to be 0. So 0 is CV natural log T2 over T1 plus gas constant R natural log V2 over V1. Then we can move 1 to the other side. So let's move this one to the other side. This equation becomes CV natural log T2 over T1 is going to be minus R natural log V2 over V1. Then we have CV in front on the left-hand side, minus R in front on the right-hand side. So why don't we divide each term by CV, trying to make it less complicated. Then the left-hand side is going to be just a natural log T2 over T1. And the right-hand side is going to be minus R over CV, natural log V2 over V1. Then, what is this R? What is the relation between R and CV? So here is, we are going to talk about specific heat relation that we were about to study in chapter 3. So specific heat relation is pretty simple. There are only two equations. Gas constant R is going to be Cp minus Cv. And the ratio between Cp and Cv is called kappa. Not K, kappa, Greek letter, Cp over Cv. Then we have this R here. Then R is going to be Cp minus Cv. Okay. So Cp minus Cv is going to replace this R. Then this equation becomes natural log T2 over T1 is going to be Cp minus Cv minus Cp minus Cv over Cv natural log V2 over V1. Oh wait, Cp over Cv is kappa. Cv over Cv is going to be 1. So this one becomes Cp over Cv, which is kappa, minus Cv over Cv 1, and we have a negative sign in front. What is minus natural log V2 over V1? It's going to be natural log V1 over V2 minus natural log x2 over x1 is the same as natural log x1 over x2. Just for your information, then this equation becomes natural log T2 over T1 is going to be kappa minus 1 natural log V1 over V2. Then the next relation, natural log A natural log B is going to be natural log B to the power A. We know that, right? So this kappa minus 1 can jump on top here. So this equation becomes natural log T2 over T1 is going to be natural log V minus V1 over V2 to the power kappa minus 1. Whatever inside this natural log should be the same. So this equation becomes T2 over T1 is V1 over V2 to the power kappa minus 1. So this is the temperature volume relation when we have an isentropic process. So if you have an isentropic process, then you can calculate, you can study the relation between temperature and specific volume by using this one equation. Any question? Then we have one more equation, this one here. So let's study this equation for an isentropic process. So this time 0 is Cp natural log T2 over T1 minus R natural log P2 over P1. We can move this one to the other side. Then divide by aspect here, Cp. Then the equation becomes natural log T2 over T1 is going to be R over Cp natural log P2 over P1. Then, according to this specific heat relation, R is going to be Cp minus Cv over Cp natural log P2 over P1. What is Cp minus Cv over Cp? So this one becomes 1 minus 1 over kappa. So this equation becomes natural log T2 over T1 is going to be 1 minus 1 over kappa natural log P2 over P1. Then this one can jump on top of this pressure. So it's going to be natural log P2 over P1 to the power 1 minus 1 over kappa. Then these two should be the same. So we have an equation here. P2 over T1 is going to be P2 over P1 to the power 1 minus 1 over kappa. So this is the temperature-pressure relation. Then T2 over T1 is this one. And again, T2 over T1 is this one. So this pressure should be the same as this specific volume. So from these two, we get one more equation. P2 over P1 to the power 1 minus 1 over kappa is going to be this one. V1 over V2 to the power kappa minus 1. Then you can simplify this equation. Then you get P2 over P1 is V1 over V2 to the power kappa. So these three are the equations that we can use for an isentropy process. So many equations today, right? So what you need to do, write them down on your formula sheet and explain, when to use these equations. So you can use these three equations whenever you have an isentropy process. So when entropy remains constant, then to study pressure-volume relation, this one, temperature-pressure, this one, temperature-volume, this one. But there is only one assumption. We got these three equations assuming that specific heat is constant. So these three equations are only valid when we assume specific heat is constant. What about if we cannot assume constant specific heat? Then we have to use this equation. Then can we use these three? No. So these three are only valid when we have constant specific heat. So this is the assumption. So we studied 1, 2, 3 equations to determine entropy change, 1, 2, 3 equations for isentropy process, and we have one more equation left over before we solve a problem. One more equation. So these three equations can be used for an isentropic process assuming constant specific heat. Then what about another isentropic process, but you cannot assume constant specific heat? That's a problem, right? Then let's see what can we do. Variable specific heats. Then if you have a variable specific heats, you can use this relation. P2 over P1 is going to be PR2 over PR1. V2 over V1 is going to be VR2 over VR1. So what is PR and VR? You can find these two from property table. So that means if you know you have an isentropic process, the ratio that you can find from the V2 and V1 is the same as VR2 and VR1 that you can find from, let's say, pressure, temperature, or from another property using a table. Then, but don't worry about that. We are not going to use this one in this chapter. When we go to chapter 9, we are going to, use these relations in chapter 9. So we will have several problems to solve together, when we go to, the chapter 9 in December. So done now. So that's everything about how to study entropy for an ideal gas. Then let's solve a few problems together. How many problems left over? One. Just one problem, two problems. And then isentropic efficiency. So we have two problems to study, how to evaluate entropy change for an ideal gas. And we have isentropic efficiency and entropy balance. Yes. Yeah, not today. The exam is going to be 12. Yeah, on Blackboard, I sent an announcement that the exam is going to be not this Thursday. Good for you, right? I had some of that. Reminder, go to boat, go to boat. I got the 10 course yesterday. I already bought it. Huh? Yeah, every day, every hour. I just got another, the spam call. So they only make, this cell phone company rich, right? Okay, so our second exam is going to be next Tuesday, right? Anybody having a conflict? No one. Everyone is happy, right? Everyone is happy. You know how many emails that I sent to you? 2 polls and a lot of emails, right? Now, everything is clear. We are going to have a second exam on 12th of November. No one has a conflict, right? Okay, good. So everyone is happy with that exam date. I have 100% customer satisfaction. An insulated piston cylinder device initially contains 300 liters of air at 120 kilopascal and 17 degrees Celsius. This air is now under heating process for 15 minutes by a 200-watt resistance heater placed inside the cylinder. Okay, and the pressure of air is maintained constant during this process. So it's a constant pressure process. Determine the entropy change of air, assuming constant specific heats and a variable specific heats. So let's do that. To solve this problem, we need to know the initial temperature and the final temperature. So what is the initial temperature? 17 degrees Celsius. What is the final temperature? We do not know. So the first part of this problem, the first part of the solution should be, finding the final temperature. So there's no relevance to, the entropy. So we just need to find the final temperature. Do we need to study entropy balance equation? No. If you want to study the final temperature or any other property in the system besides entropy, you can use energy balance equation. So let's use energy balance equation for this air to determine the final temperature. Okay, let's do that. What is the energy balance equation? There are two energy balance equations. One is for a closed system. The other one is for an open system? Is this a closed system or an open system? It is a closed system. Why it is a closed system? Because the piston cylinder device is completely closed? Not necessarily. It is a closed system because the mass of air remains constant. So when mass is constant, closed system. When mass is not constant, then an open system. So let's study this problem. Okay, so we have a closed system. The energy balance equation is Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1 plus moving boundary work. This is the general energy balance equation, but this time we are not going to use this equation because we can simplify the right-hand side. If you have a constant volume process, the right-hand side is going to be mass times U2 minus U1. If you have constant pressure process, then the right-hand side is going to be mass times H2 minus H1. And we have a constant pressure process. The pressure of air is maintained constant during this process. So we have a constant pressure process, so this is the right-hand side. So the left-hand side is Q in plus W in minus Q out minus W out. And it says that insulated piston cylinder device. So you can neglect Q in, Q out, and there is a resistance heater is providing energy to the system. So we have a W in. We don't have W out. So how can you determine this W in? This W in is what? It's a 200 watt resistance heater. So W in is what? 200. It's going to be mass times, how do you determine H2 minus H1 for air? We can use a specific heat, Cp T2 minus T1. So this is how you determine, we solve this problem. Am I right, or there's a problem here? Is this correct or not? It's not correct, right? We know that. Then what is the problem? What is not work? What is power? So how to get work? What multiply by height? Height, yes, second. So multiply by how long the duration of this process. So that is 15 minutes. So you're going to write 15 minutes here? No, 900 seconds. 900 seconds. Then you get a complete energy balance equation. What about this mass? Do we know the mass? Oh yeah, we have a 300 liters. So can you say, then how can you determine this mass from 300 liters? 300 liters, liter is a volume. So if you want to determine mass from a volume, we need to know the density. Or you can use energy balance, ideal gas equation. PV is MRT. So what is this P? 120 kilopascal. What is this volume? 300 liters, and 300 liters is 0.3 cubic meters, because 1 cubic meter is 1,000 liters. So this one is 0.3 cubic meters, and mass is the unknown. Gas constant R of air is going to be 0.287 kilojoule per kilogram degree Celsius, degree Kelvin. Then how do you determine this R? Just for your information, universal gas constant divided by molecular weight, and universal gas constant is always 8.314 kilojoule per kilomole Kelvin and molecular weight can be found from table A1. And what is the temperature? 17 degrees Celsius. So I'm going to write 17 degrees Celsius. Not anymore. We all know we need to use Kelvin, right? So instead of 17, it's going to be 290 Kelvin. So from this, you can determine the mass of the system. And what is the mass? 0.4325. So this mass goes here, 0.4325 kilogram. What is the temperature? Initial temperature, 17. So let's say 290 Kelvin. Then, can you determine the final temperature? Yes, if you know specific heat. Then where is the specific heat? Specific heat is here, Cp. So what value are you going to use? Just randomly select one of them? You can't. You need to use the specific heat at the average temperature. So what is the average temperature? Sounds pretty simple. We just need to calculate the average temperature and find the value and put this value in the equation. Sounds pretty simple. Then what is the average temperature? Unfortunately, we do not know the average temperature because we do not know T2. But what can you do? You are going to use an iteration method. What is iteration method? We're going to assume first guess. I'm going to guess T2 is going to be some number and then do the calculation and to confirm if my guess makes sense or not. So one number. I think there is a temperature increase because there's an electric resistance heater inside providing energy to the system. So let's say T2 is going to be 310 Kelvin. You can pick any number. You can pick any number. 300 Kelvin, 400 Kelvin, 3000, even 3 million Kelvin. Any number is fine. Make sure that the average temperature available here. So I'm going to assume T2 is 310. Then what is the average temperature? T average is going to be 310 plus 290 divided by 2. That is 300 Kelvin. So what is the specific heat, Cp, at 300 Kelvin? 1.005 kilojoule per kilogram Kelvin. Then what do you want to do? Yeah, now we are going to use this specific heat to solve this energy balance equation. So let's do that. I have a calculator here. And where am I? 200 times 900. Oh, I put the wrong number. 900 and divided by the mass of the system, 0.4325, and divided by specific heat, 1005. Oops, I deleted. Let me do it again. 200 times 900. I don't like this calculator. I prefer Microsoft Excel. That's the best software in engineering. Even though you perform any experimental study, Excel is the best. Even when you run a simulation, Excel is the best. You run a simulation, got the data point more than the million time steps, and this is imported into an Excel, and it do all the post processing. I don't know why I said that, but anyway, I'm not working for Microsoft. So 0.4325 and divide by, oh, I forgot divide by 1005 plus 290. Okay, I got 704. So if you do the calculation, you get T2 from this equation, 704 Kelvin. So that's how you determine the final temperature. Am I right? No, you assume that the final temperature is 310 and what you got is 704. That doesn't make sense. So your first guess is wrong. Then what do you want to do? You're going to do it again. Okay, I made a mistake. That's no problem. We can just do it again. Second guess. This time, pick another random number. No, this time we are going to use the answer from the first iteration. 704 is going to be our second guess. 704 Kelvin. And then we do it again. Then what is the average temperature? 704 plus 290 divided by 2. Then you get specific heat at the temperature. Then you solve it. And what are you going to get? T2 is going to be 698 Kelvin. Now, your guess is 704, and the answer is 698. Are they close? Yes. So you end iteration here. So the final temperature is going to be 698 Kelvin. So once you determine the final temperature, now it's time to determine the entropy change. So let's determine the entropy change of air, assuming constant specific heat. This is the equation. These two are the equations that we can use for constant specific heat. So which one? We know process is constant pressure process. So we have information about pressure change. So selecting the second equation makes sense. So we are going to use this equation. So I'm going to use this equation. S2 minus S1 is Cp natural log T2 over T1 minus R natural log P2 over P1. That's how you can determine the entropy change. Am I right? Not necessarily. We're calculating the change in specific entropy, not the total entropy. So if you want to calculate the total entropy change, you need to multiply by the mass of the system. The mass of the system. Then what is the mass of the system? 0.4325. So this one is 0.4325 kilogram. What is the specific heat that we used here? 1.02. 1.02 kilojoule per kilogram Kelvin. And natural log, what is the final temperature? 698 Kelvin. What is the initial temperature? 290 Kelvin. Then gas constant R times natural log P2 over P1. It's a constant pressure process. So P2 is the same as P1. So what is the natural log of 1? 0. So you can calculate entropy change. The total entropy change is going to be 0.387 kilojoule per Kelvin. That's when you assume constant specific heat. What about if you assume that it's a variable specific heat? Then you can use this equation. So let's assume variable specific heat. Mass times S2 minus S1 is going to be mass times S degree 2 minus S degree 1 minus R times natural log P2 over P1. By the way, we know this one is 0. But where can you find S degree? From table A22. Then how can you find S degree? Depending on the temperature. So what is the initial temperature? 290. So what is S degree? 1.668.1.66802. So this one is 1.66802. What is the final temperature? 698. What is S degree at this temperature? 698 is between these two numbers. So S degree is going to be between these two numbers. How to determine the exact value? By using linear interpolation. So if you do, we get 2.5628. 2.5628. So these two are from table A22. Then we get the change in total entropy change. And the change in total entropy, that is 0.387 kilojoule per Kelvin. Any question? It's not very difficult, right? And let's look at the second problem. This time we have argon is compressed in an isentropic process. Oh wait, it's an isentropic process. We have a pressure and temperature at the initial state. We have a pressure at the final state. So we know how much change in pressure. We know the initial temperature. We want to determine the final temperature. We can do that. How can we do that? It's an isentropic process. If you have an isentropic process, you can use these three equations. What do we know? We know how much pressure changes between the inlet and the exit of the turbine. We know pressure changes. We know initial temperature. Can you determine the exit temperature? Yes, you can. So the equation that we are going to use is this one. T2 over T1 is P2 over P1 to the power 1 minus 1 over kappa. Then what is P1? 2 megapascal, 2000. What is P2? 200 kilopascal, 200. What is kappa of argon is going to be 1.667. 1.667. What is the temperature? In the inlet temperature is 500 degrees Celsius. Can you determine the exit temperature? Yes, you can. Is that right or there's a mistake? Yeah, Kelvin. Too many times, right? 773 Kelvin. So you can determine the exit temperature. The exit temperature is 308 Kelvin. What is the work produced by this turbine? How do you determine the exit temperature of a turbine? By using energy balance equation. What is the energy balance equation? Q in plus W in. By the way, this is a steady state open system. So you can say Q dot W dot plus M dot at the inlet. I'm going to say inlet is number one. It has enthalpy, kinetic energy, and potential energy. It's going to be Q dot out plus W dot out plus M dot at the exit. This one has enthalpy, kinetic energy, and potential energy. Then we can neglect kinetic energy change, potential energy change. Turbine is the device to produce power, not consuming power. It says isentropic process. That means there is no heat transfer, because when there's a heat transfer, entropy changes, right? So we assume that there is no heat transfer. We have the rate of enthalpy at the inlet, the rate of enthalpy at the exit. So the energy balance equation is, before we talk about energy balance equation, let's move this one to the left-hand side. Then the equation is going to be M dot H1 minus H2 is W dot out. What we want to determine? We want to determine the work produced by the turbine. Which one is that? This one. Then, do we know the mass flow rate? We do not. Then divide by M dot. Divide by M dot. Then what do you get? H1 minus H2 is M dot times specific, the work. So this W is going to be mass times energy transfer by work per unit mass. And we have a dot on top of it. Dot divided by M dot. So you can cross them out. So what do we have? The energy transfer by work per unit mass. That's what we want to determine. Then that is H1 minus H2, which is Cp times T1 minus T2, is this lowercase work out. So what is the specific heat? This one, 0.5203. Then what is the inlet temperature? The inlet temperature is 500. Then what is the exit temperature? Exit temperature is 773,308. Can you determine the energy transfer by work produced by this turbine per unit mass? Yes, you can. This one. That's how you solve this problem. There's a value here. This one is wrong, so don't trust this number. So many errors in your textbook solution. So that's everything for today. Any question? So this Thursday, today is not Thursday, right? So this Thursday, we are going to, continue from here, studying isentropic efficiency and entropy balance equation. We are going to spend 10 to 20 minutes to review what we studied to prepare for your next exam.